We're looking at the graphical part of Carnot cycle. So we have a basic understanding of Carnot cycle, right? So yeah. So this represents a Carnot cycle. So we have the piston going up and down, and we get to vary what is happening at the bottom. And when we observe the pressure and volume, it takes the following curve. So what we are trying to understand is how is this varying and what is the graph about and so on and so forth. Quite a few things to discuss. So let's start by one. So first thing is we are looking at a PV diagram. So we are making use of an ideal gas, right? And then what else can we tell? So then we have this to be moving in this way. Let me complete the diagram. Yeah. So it starts from say 1, goes on to 2, then we have 3, and then we have 4. So those are the key points. So we have the system moving from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So thus making it a closed loop. So whenever you have a closed loop in such graphs, what do we call it as? It's a cyclic process. So cycle returns to the starting point, thus making it a cyclic process, meaning the initial and the final state is same. So you can tell delta U is equal to 0. For one complete cycle, delta U is equal to 0 for complete cycle. Now, second thing that we can tell is cycle has 4 distinct and identifiable process, right? 1, 2, 3, 4. And we know this. This is isothermal, expansion. This is adiabatic, expansion. Because why is this expansion? Volume is increasing. This is isothermal what? Compression. And this is adiabatic compression. Agree? Isothermal, adiabatic, isothermal, adiabatic. This is expansion, expansion, compression, compression. Quite simple. So 1 to 2, a temperature is maintained, say TH. Okay, so temperature at 1. Now we will be patterning for space. Temperature at 1 and 2 will be TH. While the temperature at 3 to 4 will be, temperature from 3 to 4 will be TC. And from 1 to 2, there's a transition. So from 1 to 2, there's a transition. So that's about temperature. What else can we tell? Volume is increasing, increasing, decreasing, decreasing. So I think we are done. Yeah. In this case, there is energy coming in. So we have energy coming in and you have it going out. In this space, it will go out. It will start from here and yeah. Technically, the entire energy will come in at this space and energy is out around here. Right? So herein, the system is taking in energy. I'm just trying to talk about this. So herein, the energy is coming in, right? So this part, the energy is coming in. And this part, the energy is going out because there is a cooler region, right? There's a sink, cold sink. So it will go out. That's one thing. This represents work being done by the system. This represents work being done on the system. So that's one more thing that we can be clear with. This is on the system. This is by the system. This is work done by the system. So what else can we tell, guys? I think, yeah. So since we are looking at this is a clockwise work, so we have seen this. Whenever we have clockwise work, your engine produces work. Your engine produces. So why is it so? And a detailed explanation about the area under the curve, all of that is done. So as I mentioned before, I don't repeat things. So that will not make sense because there's a lot of interconnectivity and this set of videos are themselves pretty long. So if I keep going back to the same thing, it doesn't make sense. Right? And what else? So the entire system is working between two temperature level. So in my diagram, I'm talking about TH and TC. So TH is your hot reservoir and TC is where your cold reservoir is, right? So that is one more thing that we can be clear with. This is the temperature of hot reservoir and TC is your cold reservoir. Okay, what else can we talk about? So isothermal runs between those two reservoirs, right? While your adiabatic helps in jumping from one reservoir to the other reservoir temperature. Okay, so isothermal keeps the temperature constant, while adiabatic process helps us jump from one level to the other level. So that's one thing that we can understand. So the area enclosed shows that the net work is done by the system. So all of that, this region gives an area work done by the system. That is one thing. So I just want to talk mainly about the curve now. So why is it shaped like this? It's not like this. It's something like this. So I want to talk about the shape. So I'll give you guys a hint. So you guys can make sense out of actual graph. So yeah, for your exam, this is good enough. We have pretty much covered all the things about graph over here. But out of my curiosity, I just want to link it to the shape. See, here I am showing you guys the isothermal graph, pressure volume graph, wherein I can vary the temperature. Say this is TH, sorry. So this is TH. TH, can you see that TH is something like this over here, right? The graph is something like this. And for TC, it's below. So can you see that TH operates when it comes to the cycle? The TH is over here, this part. And can you see the graph? So TH is something like this. Can you see that graph? It's shifted to the right, and it's something like this. So between this region is where your isothermal process is at a higher temperature. And one more place wherein the cycle operates is at a lower temperature and it's isothermal. And can you see that this part, as in when the volume increases, the pressure is less. And can you see it's almost parallel to the x-axis? Can you see this? This is almost parallel to the x-axis. So between this extreme temperature, for example, if it operates, this is the result. Then let's look into adiabatic. So adiabatic, as in when the internal temperature varies, can you see how the graph acts? Okay. So this is at higher internal temperature. This is at lower internal temperature. And can you see that how the graph varies? And so this curve. So combined version is this. For a given temperature, your isothermal is above the adiabatic. Your isothermal, right? The volume is more than one over here. So you can see that isothermal is over the adiabatic. Of course, in adiabatic, the temperature varies, and so it will not remain the same, but I'm just wanted to show you guys that isothermal is above adiabatic, and so all of this put together, you end up with this graph. Okay, again, you need not know that per se. Actually, you should know, but yeah, you need not know the details. You know what you should know. Let me not tell that you should not know. You should have it in your head. So this is the reason the cycle looks so. Why not? Right? Okay, so yeah, we are looking at Carnot cycle, which is part of Carnot engine. Basically, Carnot cycle helps us understand, break down, and understand Carnot engines working. So we have the structure over here, and it goes through four noticeable cycles. And graphically, we are looking at this. So 1, 2, 3, 4. The first part of the cycle, we can tell it's isothermal expansion. Second part is adiabatic expansion. Then it's compression. So third part is isothermal compression. Fourth is adiabatic compression. So there are quite a few things happening. When regarding to temperature, we have to make a note of it. In regarding to energy coming in, energy going out, we have to make a note of it. Work being done by the system, work being done on the system also has to be taken note of. Because it's a full-fledged closed loop and we are talking about an ideal scenario, delta U is 0. Because it's clockwise, engine produces work, right? Such facts we need to know. And yes, all of this is explained before and you should be able to understand it. Don't take it as, you know what, okay, this is it and I have to remember. It's not the case. And it operates between two different temperature. And shifting from one temperature to other temperature, your adiabatic process helps in with that. Okay. And TH and TC is your hot and cold reservoir. Yeah, that's good enough for you guys to know.